Hi everybody, welcome to Mr. Lehan Teaches You Stuff. This is Grade 10 Optics Lesson 4, the ray model of light. So in the ray model of light, as opposed to the wave model of light, light is depicted as traveling in straight lines away from the source. And you can kind of see that in this photograph here. This shows how light would be depicted in the ray model of light. We've got the sun hiding behind a tree, and lots of straight lines of sunshine coming off of the sun going in all different directions. So that's basically how light would be portrayed in the ray model. And the ray model of light helps us to understand why lights are brighter when you're closer to them. So take a look at these two pictures. In the second one, the flashlight's a lot closer to my face. In the first one, if we draw in some light rays coming off of that flashlight, they're hitting me there in the face. In the second one, though, you'll see that more of them actually hit me. The reason why this is just because it's closer and they haven't had a chance to spread out as much. So because more of them are hitting me in the face, it's more concentrated. More of them are hitting me in the eye, which means my eye is seeing more light, which means it's brighter. So this is how the ray model of light can help us explain why lights would be brighter the closer we are to them. Now we'll look at what happens when light strikes an object. If the object is transparent, the light rays will easily pass right through it. So in the case of this window, light rays just go right through. So things that are glass, some plastics, things like quartz or crystals, these things are transparent and light will just pass right through them with no problem. If the object is translucent, like this cutting board, that I propped up next to this toy fire truck, the light rays will go through, but they get scattered along the way. So the light comes to the back of the cutting board here, it hits it, and then it kind of gets scattered in all different directions. So the light comes through, but it's not making a clear image. You can't really tell what's behind it, except, of course, you know that it's a fire truck because you can see the other half of it. But it's hard to tell. You can see brightness, though. It's still light coming through, but it's not necessarily a perfect image of what's behind it. And then, of course, we have objects that are opaque. So when it's an opaque object, like a brick wall, the light rays are absorbed or reflected, and none go through the object. So light hits the wall and just sort of bounces off in all directions. If you were on the other side of this wall in an enclosed room, you would not be able to see that light because it's not going through the bricks. Alright, now we'll take a look at shadows. When an object is closer to a light source, it creates a larger shadow. So if we turn on this flashlight, this tennis ball will make a shadow on this piece of paper, and it is this big. Now if we take another tennis ball and we move it closer to the light source, closer to that flashlight, it's going to make a shadow that's that big. So you can see the shadow got larger than the first shadow. Now the size of the light source will have an effect on how blurry the shadow is. If the light source is large, the shadow will be less defined with blurrier edges. So in this first photograph, I had a somewhat larger light source. In the second photograph here, I have a much smaller light source. It's a point source of light, and the shadows have very sharp edges, and they're very well defined. Now we'll take a look at the difference between the umbra and the penumbra. The umbra is where all the light is blocked, and the darkest shadow can be found. So if you hear umbra, sort of think umbrella, and how umbrellas block the rain. Well, the umbra is where the light is blocked. So right behind that tennis ball. But the light that comes out of the flashlight isn't all coming out in a straight, perfect line, unless your flashlight is a laser. It kind of goes all over the place. So instead of just having the umbra, we also have the penumbra, which is the lighter part of the shadow that goes around. So because light can kind of cross over and go from one side of the flashlight to the other, it creates a penumbra, which is a lighter part of the shadow, which is around the tennis ball. So that's the penumbra. And when we talked about how you'll have less defined edges on shadows if the light source is bigger, that's because of the presence of a penumbra. If there was only an umbra, it would be like a point source of light, right? If we had a really, really tiny little flashlight that was very bright, you'd probably just have an umbra. You wouldn't have any light crossing over, creating a penumbra. Reflected light. In something called regular reflection, all the light rays strike the surface of an object and bounce off at the same angle. And this allows you to see a reflected image. So regular reflection happens in mirrors, shiny metal, windows, things like that. So the light hits the mirror, let's say, and then it bounces off and it maintains its shape and everything so that you can understand it when it hits your eye. You can still see that, yes, that's a tennis ball I see in that reflection. Now in diffuse reflection, the light rays will hit the object and will be scattered in all directions. What this means is that any light coming off that tennis ball, light bouncing off the tennis ball, when it hits the paper, it doesn't get reflected all together towards your eye. It hits the paper and then it gets scattered all over the place. Now this means that there's not going to be an image formed that you can see. So this means that there's no image, but the object is illuminated still by light and therefore visible. So you can still see that piece of paper because light from all over the room in random directions is hitting that piece of paper, and randomly those rays are bouncing off and hitting you in the eye. But there's not going to be any image form because the light rays are coming from everywhere. So that's why you can't see your reflection in a piece of paper or on a shoe. So that's it for this video. Tune into the next video when we take a look at reflections.